So now let's use our equation for the momentum to try and work out what pressure these electrons will exert. And once again, we're going to do this in a very approximate way. So once again, let's imagine we have a box, and there's one side of the box. Now each electron, let's assume that every electron is going either this way or that way, or vertically, or in and out. So 1/3 of the electrons are going back and forth this way, 1/3 are going up and down, and 1/3 are going front and back. This is an approximation. Of course, electrons are going in all sorts of directions, but it's not going to be too bad. So that means the number of electrons going this way that might hit this wall is going to be 1/3 of the total. So let's zoom in on that wall. So here's the wall, and we've got the number of electrons, 1/3 of the total, which are going either this way or that way. Now what is pressure? Pressure is just the combined effect of the impact of all these things on the wall. So every time an electron bounces off the wall, it exerts a force on the wall exerts an equal and opposite force on the electron. So what we want to do is work out the cumulative effect of all those tiny electrons bouncing off the wall, because that will be the pressure, the force on 1 square meter of wall. Now the way we can work this out is that force is the rate of change of momentum. So if we can work out the momentum of all the electrons that are going to hit 1 square meter in a given time, and they'll bounce off opposite, that will tell us the total amount of momentum that changed in 1 second, and that will be the average force. Okay, so how many electrons are going to hit this wall in a second? Well, it's going to be all the ones heading this way. The ones heading that way are not going to hit the wall, and they've got to reach there within a second, which means we can draw an imaginary line around here, where this is equal to velocity times the time, which is 1 second, and anything in there will have to be fast enough to hit the wall. The ones out there won't hit the wall the second they hit the wall next second. So what's the volume here? It's going to be just the velocity times the area, which is 1. How many electrons are going to be coming in? So it's going to be the pressure. It's going to be the number of electrons that are going left to right, which is 1/3 of the total. The rest are going up and down or in and out, so they're not going to hit this wall. But only half of these are going to be going in the left direction, so we've got to have another half. Then times the number of electrons per unit volume times the volume, which is 1 by 1 by v. So that's v. But each electron that bounces off reverses. It used to have a momentum p this way. After it bounces off, assuming it's elastic collision, it'll have a momentum the other way. So the change in momentum of each is going to be 2p. I should say this is a capital P, that's the pressure. This is a small p, which is the momentum. It's a bit confusing, I know, but we'll try and make it clear. So the pressure is the rate of change of momentum, comes out as 1/3 the number density of electrons, typical velocity, and typical momentum. Okay, now we know the momentum. We calculated it up here. What about the velocity? Well, if they're not going close to the speed of light, then the equation for momentum is just mass times velocity. If they are close to the speed of light, we'll come back to it. There's a gamma factor in here, but for the moment, let's assume the electrons are nowhere near the speed of light. So that means velocity is going to be the momentum divided by the mass of an electron. So if we plug that in, we find that the pressure, I'll write that in full so we don't get it confused with P for momentum, is 1/3 number density of electrons, velocity, which is, rearrange this, that's going to be P over typical mass of an electron, times momentum again, momentum coming from over here, And if we substitute in our equation for the momentum, we get that the pressure is equal to h bar squared over 3 times the mass of an electron times the number density of electrons to the 5/3 power. Okay, now there's one extra complication we need to put in here, that we don't often know the number of electrons. What we know is the density of the material. So what is the number of electrons? The number of electrons in a given volume is going to be the density divided by the mass of a hydrogen atom. That would tell you how many electrons there were if it was entirely made of hydrogen. But it's not made of hydrogen. This is a carbon-oxygen thing. So we need to correct it for the fact the atomic mass. So we put an A on the bottom. So for example, if it was carbon, that would be the atomic mass of carbon. So each carbon atom weighs 12 times the mass of hydrogen, so we're going to get 12 times its electrons. But also carbon has 6 electrons. Well, let's assume every single electron's been knocked out because it's so hot they've all been ionized. So we've got to put the atomic number up the top. So in this case, it's the density divided by the mass of hydrogen divided by the atomic mass, 12, multiplied by the number of electrons, 6. So this is going to be, for a carbon or oxygen, that's going to be about half the density divided by the mass of hydrogen. So we can plug that into there. The answer we get turns out to have all the right functional form, but to be wrong by about a factor of 5. If you did a more careful calculation, you actually get a value of the constant here that's about 5 times bigger. So in fact, the true equation for the pressure in a situation like this is the rather unwieldy So our simple calculation got all the functional form right. I got the h bar, the me, and all these things right. Just the constant comes out a bit different if you actually do the proper calculation with the electrons going in all directions. The most important difference actually is that in the real calculation, not all electrons are going at the same speed. Some are going faster and slower. So our crude calculation came out pretty close. So that is the pressure you can get from quantum mechanics.